Ladies and gentlemen, we shall now proceed with the much anticipated keynote address, The Emerging World of the Internet of Things, What It Is and What It Means for Testing. And to deliver this keynote address is a highly respected and decorated personality in the Internet of Things space. He is best known as the creator of Tron and is the leading advocate of the IoT around the world. In recognition of his contribution to the development of the industry and academia, he has received multiple awards, including this year's ITU 150 award, and he is appointed the IT advisor to the government of Japan. Please put your hands together, ladies and gentlemen, for Professor Ken Sakamura from the University of Tokyo.
Thank you for the introduction. Distinguished guests, ladies and gentlemen, good morning. I am Ken Sakamura. It is my pleasure to speak in front of the audience at Softic Asia 2015. Thank you very much, Madam Mastura. I understand that Softic is a conference for researchers of testing and developers of testing tools. Unfortunately, I am not particularly involved in the field of testing. I am now a computer architect. So my mission today is to talk on the vision of the future computing based on my experience. I hope the audience will learn from my talk what type of testing will be in demand in the future. Among the vision of the future computing, the most popular is that of the IoT, the Internet of Things. So today, I am going to talk about it. The IoT has become a buzzword in the world industry. Industry 4.0 Germany, Industrial Internet of General Electronic, or Smart Planet of IBM, etc. So many of you must have heard the phrase at least and have a vague idea of what it means. The essence of the IoT is connecting our many objects in the network. What can we do by connecting objects and sensors to the network? We can control them, of course, and run the conditions in the real world where the objects are placed. For example, we can run the extent of our temperature, humidity, air pollution, traffic condition, energy consumption, etc. Furthermore, we can create the database of such collected data for later big data analysis. By the way, let me give you a bit of my background. I am a professor at the University of Tokyo in Japan. I am also the director of YRP, Ubiquitous Networking Laboratory, and independent R&D laboratory of ubiquitous computing, or the Internet of Things in today's terminology. I am also a leader of a computer architecture project. I will explain a Tron project along my way in my speech. YRP UNL. I am the director of YRP, our Ubiquitous Networking Laboratory. It is one of the few laboratories in the world that are dedicated to the study of ubiquitous computing, the IoT in other world. I have served as the director since its establishment. As I explained in my talk, I started my own research on the IoT more than 30 years ago, and in my line of research, I helped establish UNL. My research interest from the early days focused on the vision of the IoT from the beginning. Tron project, of which I am the leader, has pursued the vision of what is called the IoT, or ubiquitous computing, since its inception. But we used computers everywhere to refer to the concept, and switched to ubiquitous computing after the phrase became popular in the 1990s. Initially, our technical goal was called HFDS, that is, highly functionally distributed systems. This is the name given by the bottom-up approach of hardware architecture. Later, when the phrase ubiquitous computing became popular in the 1990s, we switched to it. This is the name given by the top-down approach of application developers and users. It is easy to explain the notion of new computing paradigm by application-oriented name. The phrase, the Internet of Things, has become popular since the early 2000s in Europe, and we have adopted it since then. Now look at the photo of our page from a book on Tron project by Springer Verlag, note the year in 1987. Back then, I had already stated the vision of the future where many computers are embedded in objects around us in daily living, our desks, chairs, floors, walls, writing fixtures, and they talk to the network. However, there was no internet then, so the network in the figure was open-ended. Now let me show you a video clip of Tron Intelligent House built in 1989.
The first Tron Intelligent House was built in Tokyo back in 1989. Let's take a look at some of the features of this pioneering house. The floor space was 333 square meters. Basic components of the house, such as windows, were embedded with computers, sensors, and actuators. The house was built to realize the house of the future, when such components in the house would be connected via a communication network. The design of the computer system and the architecture of the house was done by Ken Sakamura. The house used natural material such as Japanese wood and stone, and had a simple and modern design. There is a staircase in the middle of the house. Other rooms can be viewed across this open space. This design facilitates communication among family members. The dining room is colorful and well lit. Quiet bedrooms guarantee comfortable sleep. The children's room overlooks the garden. There is a semi-open space, an indoor garden, when you come down the stairs from the second floor. To let fresh air inside, windows are automatically opened when there is a good breeze outside, and closed otherwise. A weather sensor helps manage the opening of windows. When you go out, all doors and windows are locked automatically once you push the "Leaving the House" button. Air flows below the eaves and beneath the roof to release heat from the top of the roof. The stronger the sunshine becomes, the more air flows, which keeps the temperature from rising too much. An intelligent kitchen helps the occupants to cook delicious meals. A central island with a sink provides efficient workspace. A computer-controlled electric oven and refrigerator line the wall. A very powerful electric oven allows the cooking of Chinese dishes. A range hood automatically extends for ventilation once you start to use the range. Let's look at the cooking support system. It offers advice on menus and videos of great chefs which will help you to prepare foods. You prepare the raw food while watching the instructional video. The proper amount and mix of seasonings is prepared automatically. Once the food is ready, you can heat it on the range. The heat is automatically adjusted to mimic what the great chefs do in their own kitchens. Japanese cypress, hinoki, is used extensively in the bathroom on the ceiling and the walls. A jacuzzi-like bubble bath comforts and relaxes you while keeping you warm. The operation of the bath follows the Tron human-machine interface guideline, just like the other switches in the house. A sauna is located next to the multi-function shower room. The windows of the bathroom use transparency adjustable glass panels. If you make the glass transparent, suddenly the bathroom looks much more spacious. This bathroom vanity makes it easy to wash your hair. The height of the faucet is controlled by a switch. There are shampoo and conditioner dispensers. The sink is kept clean by an auto clean function. The toothbrush uses a water jet. The toilet on the first floor can be operated without ever touching anything. All you have to do is move your hand over a sensor. You can also use the intercom, TV, or telephone without touching a switch. The toilet on the second floor watches after the health of the family. It analyzes your urine when you insert a test paper. Your blood pressure can be monitored while you sit. For privacy reasons, the data is stored on an individual IC card. The data can be displayed on a graph. Or the data can be sent to your family doctor via data network after encryption. You can move this party cart around the house. It can be connected to 3 stations in the house to access water and drainage and electricity. The cart is equipped with a hot plate and refrigerator and can supply hot and cold water. In the Tron Intelligent House, illumination is done by hiding lighting sources as much as possible. All of the lighting is adjustable. The switches don't simply turn on or off, but are for choosing a particular preset lighting environment. For example, you can choose a bright setting for a party and a dim setting for a cozy moment. The good night switch turns off unnecessary lighting. When people wake up and move about after going to bed, motion sensors located in the bedrooms and corridors turn on dim lights automatically. The living room is equipped with an ideal air conditioning system that uses floor heating and radiant cooling. There is a heat-absorbing panel on the ceiling, which is cooled by water. Generally, 40% of body heat dissipation is accounted for by air convection, and another 40% by radiation. Radiation cooling makes you feel cool even if we don't drop the air temperature very much. Finely controlled air circulation by fans keeps the temperature gradient small and provides a comfortable environment. Temperature, humidity, and airflow in the rooms are monitored by sensors. To monitor temperature gradients, many temperature sensors are placed at different heights in the room. The Tron Intelligent House tried a new approach to acoustics. An acoustic field creation system was installed. There are microphones in the ceiling. The sound picked up by the microphones is fed through a digital signal processing unit in order to create an artificial echo. This echo is fed to the speaker on the ceiling to give the people in the room an acoustic feeling that would be felt in a different environment, such as a room of a different size or a different situation. Many sensors are discreetly placed around the Tron Intelligent House. These sensors monitor the environment, and the information is used to provide a comfortable living environment. Weather sensors outside the house constantly monitor the exterior environment. This information is used to open or close the windows and control lighting. The plants in the semi-open indoor garden grow in artificial soil. Watering is done automatically. Two different types of plant growing systems are deployed. One uses a soil substitute called aquasoil that absorbs water well. The other is so-called hydroculture. We place plants in a pot filled with artificial stones, actually baked clay pellets, that are fed with water and air. We can simply replace plants by replacing pots directly. The Tron Intelligent House uses a computerized storage system or archive. The storage space is built underground. It houses 10 containers. You can pick out the right container by looking at the photos of what is inside. Then the container will be lifted and you can receive the object you wanted to retrieve. When you put something in a container, a photo is taken by a small electronic still camera on the ceiling, and it is registered in the computer database. As you have seen, the pioneering Tron Intelligent House was years ahead of its time.
The video has shown that the Tron Intelligent House was built based on the original concept of HFDS, which was already present at the start of the Tron project in 1984. The parts used in the futuristic Tron Intelligent House were connected to the network and provided a comfortable living environment to the human inhabitant by cooperating with other parts in the house. Today, it would have been called the IoT house when you look at its functions. A node in the house with computers, sensors, and actuators are connected to the network and build up an intelligent house as a whole. Through research such as Tron Intelligent House, I was considered a pioneer of IoT, coupled with the contribution of Tron project. I was chosen as one of the recipients of ITU 150 Award in Geneva in May of this year. ITU 150 Award were created by ITU, International Telecommunication Union, the international de jure standard organization. The ITU 150 Award were given to six. Say hello to Bill Gates, Robert Kahn, the pioneer of internet, and others, include myself. I think you have heard enough background of mine. Now you know what I am. So let me explain the IoT, Internet of Things, the application and the needs and other parts used for it. Well, let me talk about the nodes. Now about Tron project. The names stand for the Real-Time Operating System Nucleus. It celebrated its 30th anniversary in 2014, last year. This is one of the long-lasting computer projects in Japan. Its original research focus was about the embedded real-time operating system on the new microcomputers. And the target of the application for these microcomputers and embedded operating system was meant for the future IoT. The vision was there. I will describe it open architecture approach later in my talk. These are three major versions of real-time operating system that came out the Tron project. They are iTron, T-kernel, and the latest version is T-kernel 2.0. These RTOS have been used in many products. Automobiles, for example, Toyota car, musical instruments by Yamaha, printers by Epson, fax machines, data cameras, mobile phones, and spacecraft. The Japanese spacecraft that brought back a tiny trace of asteroid surface and sand and rock used Itron operating system, and later models deploy TKNL operating system. I have explained the technologies for each node in the IoT. Now it is important to have the framework to tie these nodes together in the network. I will come to the IoT application network in slightly more detail later, but it is called UID architecture based on the notion of universal ID system called UCode. It is used in many of our IoT applications. I will talk about UID architecture later in my speech. Now, before diving into the topic of the IoT, which is one of my main R&D research topics, I have a short comment for testers. This is, after all, Softic Asia 2015. But as I explained at the beginning of my talk, please don't think I am a professional taster. In my line of work, I do need testing and have experienced difficult system bugs and such. I can only give our developers' view on testing in the age of the IoT. During today's talk, you will find that testing in the IoT age becomes difficult. Why? Because you have to understand both the embedded computer systems and the network and services that tie them together. Imagine how to test functions of Tron Intelligent House, Tron House. The embedded system in the age of the IoT is no longer a closed unit. A digital camera, our typical embedded system, was a closed system, but it is today connected to the internet and talks to cloud server. Testing has to include all the players, aside from the camera unit to cloud servers in such usage. So, like I show on the page, you have to figure out how to test the new scenarios. But first you have to run the scenarios in the IoT age. So I will focus on the IoT applications first, and I'll mention the testing at the end. Today's talk is organized as follows. Today's speech slot is 2 hours. I will use video clips to keep you awake. I may skip some slides, but you can download it to a PDF file, so you can look at them later. It is easier to understand what the IoT can do for us. So I will list some IoT applications and explain what it can do for us. Then I will explain that where the success of some approaches, I will especially focus on the open approach of Tron project, which turned out to be very successful. Then I will explain testing in the IoT age, or rather the difficulties it will face. Lastly, I will explain Tron Forum and NPO organization that has promoted Tron project and its output, if we have the time. Now let us look at the IoT application. In order for you to glimpse what the IoT applications can do, I will describe successful application example in Japan. I hope you may be able to learn some hints. Oh, there are many examples for which I prepared slide. Oh, after the big earthquake in 2011, our nuclear power stations in Japan were shut down. So we needed to use alternative energy sources, wind, solar, small-scale hydropower generation plants, geothermal, and the nuclear once it is back online, etc. A smart grid is indispensable to mix the alternative power sources and still maintain a steady power supply. At an individual home, HEMS, that is a home energy management system, is being introduced to help people to monitor the electricity usage and cut down on waste. The information of smart meters is used for a large-scale smart grid control too. This is another topic. IC card are important node in the IoT paradigm. IC card can be used for a payment for public transportation. In Japan, a popular IC card for public transportation can be used for a payment of inexpensive goods at the stores now. Not needing to carry small change is very useful. Now, because so many individuals carry IC card, running or moving patterns of many people, even anonymously, is considered very useful. This is amazing video.
Japan's population is about 127 million people. With the popularity of payment cards and transportation cards, many Japanese have at least one smart card now. The whole smart card family for small amount payment and transportation tickets is used by many people all over Japan. The total number of such cards would be easily over 100 million. 70 million cards are used in prefectures including the Greater Tokyo area and its surroundings alone. The original and still foremost application of Suica cards is to use them as transportation tickets for 13 million people who live in the Greater Tokyo area. There has been a need for a system that allows the passage of a large number of people quickly in the morning rush hour at stations in big cities. It is possible to use these cards as tickets by writing the data of the ticket, commuter pass, etc. in the security area of the cards. The stored data format for ticket information has been standardized by Japan Railway Group, many other private rail services, and bus operators in Japan. So the transportation cards are interoperable all over Japan today. People can pass through the ticket gates easily by placing a Suica card on the gate readers. NFC built into smartphones can be used in place of Suica cards these days. Reservation seats now come with Suica readers to save the labor of ticket examination by conductors. Placing a Suica card with the reservation information over the reader registers that the right user is sitting in the seat. There are many drink vending machines in Tokyo. Vending machines are often targets of vandalism and theft, but in Tokyo, they thrive thanks to the relatively safe urban landscape there. They are also inside the stations, of course, and you can buy drinks by using Suica cards. Use of smart cards for payment may make vending machines popular in other countries because real coins do not have to be inside the machine. The lack of money inside should decrease the incidences of theft. Here is a baggage locker at a station. You can pay for the baggage locker at the station by Suica card. The Suica card acts as a key to open the locker when the user returns.
The next topic is infrastructure management. The IoT technology can be used for maintenance of social infrastructure such as roads or bridges and other structures that are related to roads. Here we show the schematic diagram of a monitoring system of roads, bridges, etc. Sensors embedded in roads and the structures emit data that tells us about the deformation, and this signal is picked up by maintenance cars to detect anomaly. Let us look at the video of this system.
This video shows an expressway structure maintenance management system that uses U-code active tags, or DICE. The tag is equipped with a vibration sensor and sends out a signal that shows the health of the structure. The monitoring vehicle that runs at the speed of 80 kilometers an hour can simply pick up the radio signal from the active tag and determine the position of the reported problem. This is the active tag DICE attached to a bridge structure along an expressway. Manual monitoring of structures along expressways is a time-consuming and dangerous task. The monitoring done by a running vehicle streamlines the task by collecting the position of the problem and information of the structure such as maintenance history and blueprints instantly.
Next topic is the natural disaster relief management. Natural disasters come and go. In Japan, earthquake and typhoons are major natural disasters. Open data and big data analysis can offer us helpful tips during and after our natural disaster hits. And the data from the IoT sensor node is useful. For example, our data from Honda GPS-equipped car navigation system allowed us to see which roads were clear of debris after the big earthquake. ICT can strengthen the industry. Here is an example of so-called industrial internet. IHI Corporation, our heavy industry manufacturer company, performs a fault prediction and preventive maintenance of gas or turbines used at power generation plants. The analysis is done by big data analysis of sensor data. Stopping gas turbine for an hour cost almost $1 million US, and so keeping it running all the time is our utmost goal. IHI manages to achieve 97.5% uptime thanks to the big data analysis. About half the failure can be avoided by preventive maintenance. Here is another example of industrial internet. NEC uses big data analysis of sensor data to monitor industrial plants to avoid a plant-wide shutdown. The number of sensors used at the nuclear power station thus monitored is 3,500, and hundreds of data are collected for each sensor each second. Aoyama Trading, the world's largest men's suits company in Japan, uses IC tags for quality control of imported men's suits from China. Toho Pharmaceutical uses IC tags to streamline logistics inside a big warehouse for delivering drugs to individual hospitals. Management by IC tags has become widespread.
Let's take a look at applications that put tags on objects first. Tags are placed on men's suits during the production phase. Tags are used during the manufacturing process throughout all distribution channels, in the stores, and even after the consumer purchases the suit. This kiosk terminal was placed in a retail store of Aoyama Trading, the world's largest retailer of men's suits.
And another topic is the food traceability. Our food traceability system and drug traceability system have been developed and used.
In this video, we explain some examples of food traceability systems based on U-code. The first example is for fresh vegetables. We show the tracing of how vegetables are grown and in what manner they are transported. Finally, how traceability information is provided to consumers at stores is explained. Agricultural chemicals and farmlands are assigned U-codes. Boxes of cabbages carry their own U-code RFID tags, and U-codes of farmlands and chemicals are recorded. When the cabbage boxes arrive at the cooperative warehouse, the U-code of shipped cabbage is read and a shipment record is created. Then the cabbage is shipped to the wholesale market. This is the Central Fresh Vegetable Market in Tokyo. U-code active tags are attached to boxes. Simultaneous reading of multiple ship boxes is possible. The U-code active tags have built-in temperature sensors, so we can monitor the temperature change during transport. This is a branch of KQ Store supermarket chain. Cabbages are checked using U-code RFID tags upon arrival, and a new code is assigned to each individual cabbage on the sales floor. Kiosk terminals on the sales floor can read U-code RFID tags when consumers place cabbages on the tabletop. Then, consumers can learn the traceability information, that is, by whom, when, where, and how the cabbage was grown. We can even learn the best ways to cook it, or look at the message from the farmers on the kiosk terminal. U-code traceability systems can be used for other food products, such as milk and tofu. Tofu is a cooked food made from soybean curd, and chemical agents are used to solidify it. Each ingredient is tagged using U-code, and we can learn the original ingredients by reading U-code of tofu. Milk cartons are tagged with optical U-codes for tracing. Thus, it is important to attach U-codes from the originating place onward. Here, a meat block is sliced into smaller packages. New U-codes are given to the packages. At the Co-op store in Hokkaido, meat is sliced and put into packages. They are tagged using U-code during packaging. At Summit store, meat packages are also given a U-code when they are weighed and priced. Aside from traceability information, we can offer additional services. By storing allergic reaction history in customers' credit card, we can offer safety warnings about foods the customers buy, if they may cause allergic reaction in family members, and so on. The last example is from the traceability experiment at Nihonbashi Mitsukoshi department store. Using kiosk terminal on the sales floor, customers can learn when, where, and who produced the meat, fruit, and other food packages, and how they traveled to the store. Aside from the distribution channel, the consumers find U-code traceability useful. They can use their mobile phones to access traceability information by attaching two-dimensional U-code QR optical codes to products, so consumers can check such information at home. This is a special feature of U-code-based food traceability systems.
Next topic is enabler. ICT can aid ordinary people and people with disabilities alike. Enabler is a term coined by my research group about 30 years ago to refer to ICT technology that helps people to achieve something. In the rightmost photo, a white cane with RFID reader at a tip guides a blind person to work in urban areas. This person's cane detects RFID passive tags embedded in the road and using the ID in the tag. Route guidance is provided by voice. In the middle, a wheelchair is similarly guided on the street. In this case, the suggested route avoid bumps in the road, such as curb, so that it is easy to navigate the wheelchair along the route. The leftmost photo shows the sightseeing guidance given in a foreign language in Japan. ICT can support people's movement everywhere.
Universal design. There is no doubt that the Internet of Things or ubiquitous computing can help the aged or people with disabilities. However, if we regard such technology as helping only them, the wide deployment in society can be very expensive in terms of cost-performance analysis. The cost issue can be mitigated by applying the concept and approach of universal design. Universal design in this context means simply that anyone can use the technology based on universal design. If the technology can be used by ordinary healthy people, cost per person will become lower. Guidance of the visually impaired using tags is certainly technically feasible. However, embedding active and passive tags along major roads and streets only to help them is too expensive from the point of view of cost. However, if the same technology is used by ordinary healthy people, new applications can emerge, such as neighborhood sightseeing guides, commercial usage, such as shop and restaurant guides, and public usage, such as information about nearby toilets, stations, and public buildings. Such new applications increase the population base who can benefit from the technology considerably. Based on the concept and approach of universal design, a project is being carried out under the banner of Tokyo Ubiquitous Technology Project. This project aims at turning Tokyo into a so-called U-City, which supports both ordinary people and people with disabilities. ICT support should be available in ordinary times and during and after natural disasters. One of our design objectives of a future city is to offer help, such as guidance for evacuation and safe passage to emergency shelters during natural disasters, by equipping cities with advanced functions using the ubiquitous computing technology. Please note that our approach is based on universal design. An approach that helps only people with dementia or other forms of disability is limited in the long run. We should always consider the society as a whole as the beneficiary of new emerging technologies and try to lower the cost of introducing it per capita to deploy such technology in society. We believe this approach is the only way to help people with disabilities as well as people in the general population by obtaining consensus from society for new technological deployment.
Okay, well, the basic tenet of philosophy of Tron project is that it aims at open architecture. This is very important. This is not a technology itself, but an approach the technical project, namely Tron project, has adopted very successfully, and so I wanted to introduce it to the audience today. As I have explained, such embedded computers are now in the nodes of the IoT and play important roles. What does open mean here? Open means our technical specifications and sample source codes are made available for free to the public. With this approach, the project could invite many third parties to become our part of the ecosystem. And the project and ecosystem have become very large. Besides, on my experience of Tron project over the last 30 years, I believe that the open approach is also very important in the R&D of the IoT. Tron project has shown its usefulness, especially the embedded RTOS part. Tron project also pays attention to build the total architecture of the IoT by connecting these nodes based on Tron RTOS family. I will touch our approach to the total architecture later. Let me stress this again, since the idea is so important. Open and free means the specification and source code for sample implementation are open and free and accessible by anyone. Tron RTOS TKNL is available under very liberal license called T license. Its current version is 2.0. We have heard from the industry to make it developer-friendly license. First of all, please understand that we need a license even though we release the specification and the source for free. This is to protect TKNL source code against copyright and patent infringement. Let me explain some outcome of Tron project over the 30 years. This is to show how successful its open approach has been. This is a number of supporters, which counted in December 2014. The project has been supported voluntarily by many organizations. The breakdown is 910 commercial organizations and government laboratories and 112 academic institutions. One of the most important technological outcome of the Tron project is so-called Tron RTOS family. The number of 8,233 is the number of organizations who agreed to the license and downloaded the source code. Before TKNL, iTron specification OS was released without T license. Our guess is that iTron specification OS had 10 times as many users. People from 76 countries have downloaded TKNL software. 76 is a rather large number, isn't it? The colored territories where someone downloaded TKNL source code. What surprised me, though, is a global community is using TKNL. Look at Africa. The place where TKNL is picked up. 30 years ago, there was no inquiry from Africa. When asked the people who downloaded the source code, mention for building mobile phones. The phones, the countries in Africa are looking for an inexpensive model of phones, not the grand smartphone of today. There have been simple mobile phones that were built using iTron specification operating system inside, and moreover, there is no royalty payment for TKNL, so that makes sense to people who wanted to build such phones. I will speak now a couple of pages here. As a result of this popularity, Tron RTOS family has about 60% market share in the high-end embedded systems market in Japan. These numbers are from our continuing survey at the Embedded Systems Conference. Okay, there are many more accomplishments of Tron project aside from its contribution of open and free approach and RTOS family. There are some interesting IoT applications as well. So let me skip through some achievement from Tron project. In my line of research, I built a handheld mobile device for the IoT applications we developed in 2003. Please recall that the first iPhone appeared in 2007. This is a photo of the first ubiquitous communicator UC for short, 2003 version. UC is a crucial component of our vision of the ubiquitous computing or the IoT. When sensors are ubiquitous, we need a device to read data from it for our user who roams from one place to the other. The natural goal is to have a device with an RFID reader or network connectivity to pass the data to the remote server and user interface to interact with it and Wi-Fi. The answer is UC depicted in the photo. It has an RFID tag reader, UI that uses touch screen, and it has network connectivity using mobile telephone network. I should note this UC runs on Tron RT OS family, the first version of T-kernel.
Drug packages. Systems can be built to help avoid mistakes when dispensing drugs at pharmacies or when taking drugs at home. Reading RFID tags on drug containers can help prevent the undesirable side effects of combining drugs, a common mistake. It can warn of such combinations and also when drugs expire. Next is a system to help pharmacists avoid incorrectly dispensing drugs. By reading RFID tags on prescription and drug packages at the same time, we can check whether mistakes are being made, such as missing drugs or incorrectly dispensed drugs. An IC card that holds a patient's history can be used in such a system to check for drug allergies, view and compare with past prescriptions, and more.
This is an application inside our smart house called Puppy. I will show you a video clip about Puppy later. Unfortunately, in Japan, UC did not catch people's attention very well. This is because an old-fashioned mobile phone without touch screen or applications have taken root already there. And when we presented prototype of UCs with RFID read and writer, people said, it would be too expensive, and all other negative comments. But when iPhone came out, suddenly there was a bandwagon. It is disappointed to be a pioneer something. Bringing a bulky UC terminal may not be handy all the time, so we even developed our special wearable UC too. We were ahead of commercial offering by many years. Please understand, I am now computer architect and also the designer. And smart house is one of the well-known applications of the IoT. I can honestly say that I am a pioneer in this field. You have seen the video about Tron Intelligent House. When Tron project was started in 1984, I already had my vision set on future applications of RTOS for embedded systems and new microprocessor chips. So with the help of supporting our companies, our smart house was built then. Back then it was called the Tron Intelligent House. This was completed in 1989. Everybody involved in the project found it very interesting and exciting. Visitors found it very interesting too. The prototype of now popular and famous electronic toilet was installed there. In the first Tron house was used iTron specification operating system. This is our Puppy completed in 2004 with support of Toyota. I have to stress that I am interested in the future application of computer systems that can be built using the technology which I helped develop. So now please take a look at the video of the second Tron intelligent house called Papi.
Welcome to the Tron Smart House. The security unit will warn us when something goes wrong while we are away.
There was a security alert. Please proceed with caution.
Biometrics authentication is used to open the door automatically. We can vocally instruct the elevator to come to our floor.
We now proceed to the entrance.
This piano plays tunes according to the signal from a piano in a concert hall. So you can enjoy the performance as if you were in the concert hall. This is the living room. We move to the dining room from the living room. Please note that the display on the ubiquitous communicator changes and shows only relevant items suitable for the new context. This is the kitchen. This is the refrigerator of the future. Such a refrigerator understands when, where, and who made the food packages inside. So it can warn when the food becomes stale and not good for consumption anymore. This is an application of ubiquitous computing. We can retrieve stored boxes attached with tags. We can choose a particular item and get it from the storage room. This is the bedroom. The house controls the temperature, humidity, and illumination to let the inhabitants have a good night's sleep. A house's alarm function controls the lighting so that the person moves to a shallow sleep phase just before waking up. The sleep phase is monitored by an easy-to-wear bracelet-like heartbeat sensor. The bathroom is next to the bedroom. From there, we can go to a swimming pool or sauna. The interior of the children's room is covered with Knauf panels, environmentally friendly material. This is the AV room. The soundproofing is very good. It is a small room, but echo control is done by a computer to give us a fine audio effect. This room is for tea ceremony. Ordinary Japanese houses use environmentally friendly material, tatami mats, wooden frames, etc. We would like to continue this tradition in the future. This is the car garage. This garage has an advanced function to keep the Tron house alive. The pillar you see feeds electricity to a small electric vehicle used for shopping, among other things. The Tron Smart House uses electricity. When a blackout occurs, we can use Prius, the famous electric gasoline hybrid engine car, to feed power to the house. We can connect Prius to the pillar, and Prius can feed power to the Tron house for 36 hours. It is interesting that we can use a car as a backup power source. This mechanism is the world's first. In case of a real emergency, we can escape in the car. There are many solar cell panels in the Tron Smart House. The solar cell is the so-called dye-sensitized type. We can print solar cells onto glass panels. The Tron Smart House uses environmentally friendly material so that material can be recycled when the house is torn down. The outer structure is basically an aluminum frame with glass panels. The exterior of the house is coated with titanium oxide. Titanium oxide acts as a very powerful chemical catalyst. In the presence of light, It can decompose organic material into water and carbon dioxide. In a sense, the coated surface has a self-cleaning function, so we don't have to clean the surface manually. Once again, to summarize, the Tron Smart House has been built to use as little energy as possible, to self-generate part of the used energy by solar cell panels, to use material that can be recycled. In a nutshell, this is an environmentally friendly house.
Okay, a house is just a single object in a large urban landscape. I am interested in using the computer for controlling the urban environment, that is so-called smart city. I am holding you see in my hand here, this is from our scene of a project I have conducting with the Ministry of Construction, Transport and Tourism of Japan. The ministry is in charge of map creation all over the Japan for serving points that are fundamental to map creation. The ministry has decided to include the electronic tag that carries a unique identifier, U-code, which I will explain later. By scanning the code in the tag, a person can retrieve information associated with a location nearby. I have been involved in project which embedded many computers or chips in the road. Now, the scene, the world was caught up with what I have been doing, and people call what I have done the IoT. I have been calling it ubiquitous computing. This happened around the year 2000. So let me explain some application projects which I conducted and what are now better called the IoT. This is a sensor node produced at a YRP Ubiquitous Networking Laboratory, which I am the lead director. The upper part is a solar cell. This sensor at the end of a stick can be pushed into now soil of the farm easily. It can collect information such as temperature, humidity, atmospheric pressure, etc. The sensors that can detect human monitor as well. This is at the heart of smart agriculture today. Traceability systems are good applications of the IoT. We can trace many things by tagging them with unique ID. For example, this is a real-world example of a traceability system of horseradish, which we tested. This and the next slide are the so-called U-code NFC, near-field communication tags that are placed on the lamppost along the street of Ginza in center of Tokyo. This term can be used as a basis of location-based information services, or note that this can be used underground. We have many underground shopping streets in Japan. What we have done is to attach these NFC tags in many places in Ginza, and they can be used for various purposes. If maintenance person from the local government scans this, the maintenance record can be shown on the screen. If a sightseer scans this, sightseeing information can be shown. Such multi-purpose usage scenario has attracted much attention now. Even within the house, we have our technology infrastructure to know where one is located. Knowing where you are, knowing what are in the same room, etc., allow us to build many interesting applications. Such technological infrastructure and applications are now blossoming. This is a photo from Taiwan U-Home, the third generation Tron intelligent house. There are many types of RFID tags, and this reader-writer can read many types so that one is enough for a field operation. We have built this at YRP Ubiquitous Networking Laboratory. Also, this is an important real-world IoT application. This shows the traceability of a blood-based product in Japan. Today, Japan Blood Product Organization tags product manufactured by pharmaceutical companies. This is based on the UCODE ID system, which I have developed. The accidents related to a blood product affect patient lives, so the traceability has been deemed important enough that the drug package are tagged with IC tags. So all in all, after the 30 years of my research, computer chips, chips and embedded computer system have embedded the realm of our daily living. It used to control only machines at factories, etc. And now these tiny computer nodes are connected to the network, and my original vision of HFDS, or computers everywhere, are being realized. Well, I have not explained UID architecture, the IoT application framework for the IoT very much so far. The basic idea is very simple, although implementation needs details. To get you started with the basic idea of ubiquitous ID architecture or UID architecture, let me show you a video clip.
In this video, we explore an application framework called Ubiquitous ID Architecture and what it can achieve in the field of ubiquitous computing. With Ubiquitous ID, or UID architecture, we assign a simple 128-bit ID number, a number called a U-code, to objects and places we want to identify. By itself, the U-code is meaningless. But when we send a U-code to a server on a computer network, we can retrieve information associated with it from information servers. A process called resolution takes place, and we obtain an address. Often, this is an internet URL one can access to obtain useful information. Since we use network access to obtain the meaning for each U-code, access is controlled at the network access stage. We can grant access to different information at different times, based on who, when, or where they are. The number of IDs in the ID space is 2 to the power of 128, a huge number. Even if 1 trillion people assigned unique U-code values to 1 trillion objects every day for 1 trillion years, we would still not have used up all the U-code space. With so many numbers available, no U-code is ever reused. We simply assign a new U-code ID for each identifiable different item. There are no a priori meanings assigned to the U-code bit fields, so it is relatively easy to embed shorter legacy product code systems in U-code space because no collisions of meanings assigned to bit fields are likely. Everything we want to identify, namely objects and places, are tagged. This is why we use so many different types of tags to meet application needs such as cost, physical characteristics, etc. Our approach is tag agnostic. We can use any type of tag. UID architecture builds a bridge between the real world of tagged objects and places and the virtual world of information about the objects and locations.
As of December 2014, the number of issued U-code is 120 million, about 120 million. Main use is so far our open data application, traceability, geological survey, medical application, event, etc. Well, so we are at a crossroad where the IoT is being recognized and IoT applications are built for real. What is the future vision? Where do we go from here? This is important, and so I am repeating it here. It used to be that embedded systems were closed, independent units. Digital cameras, cars, etc. were independent, for example. However, cameras can now upload photos to cloud servers. Cars can talk to the internet. Every object will be connected to the network. So a fundamental shift to application model has occurred. This drawing shows the model of web application service. Individual users have smartphones, a part device, and PCs. From there, users upload the data to cloud service. Users then obtain the result sent back. In this model, the virtual world is closed in the sense that only real-world data which people proactively upload to the network. There is filtering of human users, and the amount is limited. In the IoT application model, embedded systems are part of the network. These embedded systems include sensor node. Many people did not share this vision 30 years ago. They thought it was a fantasy in science fiction stories. Today, in the IoT application model, sensors send data to the network without human intervention at all. Temperatures and humidity of place, operating conditions of control unit of machines, unit of our factory, etc. Imagine the total amount of such data all over the world. It is huge, of course. It depends on the frequency and amount of each data. But this huge data has allowed us to discover and or infer many facts about the real world now. Remember that the parts used in the futuristic Tron intelligent house were connected to the network and provided comfortable living environment to the human inhabitant by cooperating with other parts in the house. Today, it has been called the IoT house when you look at its functions. Node in the house with computers, sensors, and actuators are connected to the network and build up an intelligent house as a whole. A smart house is a typical IoT application, and it depicts the new application paradigm very well. Let us stand back and what ubiquitous computing means. In my interpretation of the phrase, it means embedding computers everywhere. Our computers have become very small and inexpensive. So basically, any object in our surroundings can have computers inside. Some people may find the notion a little creepy, but don't worry. We have the option not to embed computers where inappropriate. The word ubiquitous means something is everywhere. when our environment is filled with computers to run the status of real world so that we can control it to benefit human inhabitants, computers are everywhere. So the phrase ubiquitous computing is an apt phrase to refer to the concept. But I think our original phrase, highly functionally distributed system, HFDS, is also appropriate here. We predicted that instead of having a gigantic supercomputer which handles the information wrong, increasingly small computers would be inside many objects and they would operate in a coordinated manner by sharing information. And the system as a whole would produce better service to human users. Whatever the name is, the vision we had more than 30 years ago finally is being realized today. The possibility of applications in the future is large and available at different scale. From the center of the figure, I have listed applications of small scale, such as automatic opening, closing, or closing of windows. At a large scale, we can use satellite photos to understand the situation on the ground and supply location-specific information. These can be used for disaster relief, planning, or early warning. The necessary thing is to run the real-world information. And one important and necessary means to do this is to embed tiny computers node in many things. The last dozen years were our feasibility study stage for the IoT. I think the next dozen years is when the IoT really sees a full blossoming of applications. For example, in Japan, Tokyo will host Olympic and Paralympics Games in 2020. The government has many plans to make Tokyo an IoT showcase, so to speak. So it will be a very interesting and amazing place to visit. But as a researcher, I am proposing an approach called Open IoT. Please note that I mentioned at the beginning of my talk that many IoT applications and prototypes are closed proprietary systems. Applications of General Electronic regarding its maintenance of turbine blades for power stations is often touted as a good example of industry internet. GE has sold turbine blades in its power station business, and the installations are more than 10,000, huge. It corrects the operation conditions, uses the data to forecast manufacture malfunctions and cut maintenance cost very much. It is useful, but it only applies to GE power stations. As a researcher, I wonder whether Open IoT is possible instead. I have taken open and free approach in the embedded systems field, and it has turned out to be very successful. Can open innovation benefit from Open IoT? So then, what do I mean by open embedded systems with this background? Let me explain the notion first by describing the closed embedded system. Take a home electronic appliance, say our hard disk recorder. It has a control panel, power switch. The buttons to select and record a program is there. A remote control unit allows you to do all what you can do on the control panel. A TV set are similar. They are now unit that we can control from the smartphones. However, these are closed embedded systems. They can be often controlled by the original manufacturer's remote control unit and the smartphone application developed by the company. In contrast, an open embedded system publishes the API, Application Program Interface, to control the video controlling and power on or off everything, so anyone's applications can control such systems in the future. Or we can control illumination lamps with computer chips with radio or connection. If such lamps are open embedded systems, you can control them from your smartphone. Of course, if anyone can turn on and off the lamps in the house, it will be like a haunted house. Passers-by may find it amusing to turn the lamps on and off. So we must turn the closed embedded system into open embedded system to make sure such actions are permitted only to authorized users. Of course, the audience will be familiar with access control. So we must establish an access control framework that is applicable to embedded devices. Otherwise, if anyone can control devices, bad things would happen. When we speak of open embedded devices, it means that there are standard set of public API, Application Program Interfaces, for the devices. It is simply technologically. With such a set of APIs, software can do wonders. In the slide, I explain what we can do if there are open embedded writing system and human motion sensor. I can tell you a philosophy when open embedded device becomes industry standard. Tron Project has tried to help people with disabilities by the use of ICT. People's disabilities comes in many different forms. Some are orally challenged and some are visually challenged. User interface of our applications, such as one that controls home appliances, often lack the support for such disabilities. There are demands for audio-based control from the visually impaired people and screen-based control from the people with hearing disabilities. Many appliances or manufacturers lack the manpower to support all these different demands. If open embedded device becomes the industry standard, someone with a skill of programming on smartphone can prepare the appropriate user interface people with a particular form of disabilities. It is not possible today. Our open approach requires a careful discussion in advance. We need a philosophical backbone, access control, and data gathering in the open IoT require the discussion of privacy versus public data, ownership, and other issues. Everybody agree that privacy is important. However, in case of emergency, public goods may have to come before one's privacy. If someone gets infected by deadly contagious disease, it is desirable that whereabouts of the person in the last few days be made public or at last made available to the medical community and public health organizations. What kind of governance of data gathered by sensors all over our surroundings should be, and who owns the data, and other issues must be discussed, and if necessary, laws and regulations may have to be changed. My main point here is that the IoT has finally arrived, and we need to establish the philosophy to cope with social situation where computer would be everywhere in our surroundings. We also have to update the legal system, if necessary, after the philosophy has materialized. How to deal with the concept of privacy and public is just one of the questions. I urge the audience to think about the type of problems your society may face if the sensors in the surroundings can theoretically make it possible to trace your moving patterns, even if it may be anonymously. Now, I mentioned the cautious words about the philosophy, the change of legal system, and such. Let me go back to the discussion on the technical side. I think the audience by now realize that what we need in the future, in the age of the IoT, is a high-level framework which consolidates and integrates the information of embedded system, is aware of context, and conduct a policy-based distributed control. It is a grand phrase, but we must find something that fits the description. For an open embedded device, one approach is to come up with a single unified API or an API that integrates all the variants of today. But it is inevitable that such an approach would fail in the long run. History has proven it many times. Manufacturers ask for the differentiation to market product differently. So a popular product comes out with functions not specified in unified API. Eventually, such integrated API's value becomes moot under such conditions. Instead of an fixed API, which would be outdated soon by the progress of technology or a new popular product that offer features not specified in API, we are trying to come up with a method to describe the API set of an open embedded device so that an application can run it at runtime and figure out how to invoke the described functions using the available API. This is a grand long-term challenge in our current research. Also, access control mechanism can't be simple in the IoT age. Access right based on the groups is necessary. Anonymous data extraction should be supported. Since the knowledge of when, where, and who are available or should be available when somebody access a device. We should be able to offer a different access setting in case of normal times and emergencies. By using cloud knowledge, we should be able to reflect regulatory changes over time. In our current research, UID architecture, which I mentioned as the IoT application framework, is being investigated or if it can be used for flexible open control of API access by cloud computers. Access control is flexible and changed by context in our scenario. I have explained UID architecture briefly earlier in my talk, but I think it is necessary to refresh your memory a little bit here. UCODE is a universal individual identification number which can be assigned to any object, prices, and concept to be identified. Using UCODE, we have developed a modeling framework to describe the real world. This framework is important for ubiquitous computing, and the access control I have explained. So I'm going to explain a little bit about the modeling framework. The modeling framework is called UCR. UCR, R stands for relation. In this model, a tangible object, places, a location in space, and concept, a virtual object, are assigned unique UCODE. The key to the modeling in UCR is we assigned UCODE to relationship in the real world. Triple of UCODE 1, UCODE 2, UCODE 3 represent the relationship. UCODE 1 has a relationship of UCODE 2 with UCODE 3. I will show you a very brief video that explains the notion of UCR.
We will now explain the use of UCODE relation in food traceability systems. Animals are managed by using UCODEs individually. Their life history is recorded. When meat is shipped, each shipment is assigned a new UCODE, and the relation with the original UCODE of the animal is recorded. When meat is sliced and put into smaller packages for sale, a new UCODE is assigned to each package, and the relation with the original UCODE of the meat is recorded. All UCODEs are related in the UCODE relation database. When the food ingredients are processed to produce food products, a new UCODE is again assigned to the final product. The final UCODE of the food product and the UCODEs of the original ingredients are related to each other in the UCODE relation database.
This is an example of UCR, UCODE relation for objects. The previous slide shows the use of UCR, UCODE, relation for objects. This slide explains the use of UCR for place. Today, we have further updated UCR into so-called UID architecture 2.0. This incorporations the UCR and enhances the original UID architecture's simple resolution mechanism with multiple types of database for application needs. We have no time, so you can learn more details by looking at the yellow handout. Now, finally, the favorite topic of the audience. Mind you, I am not a testing professional, but just an established researcher who need testing or prototype and working systems. Let me explain my take on testing for the IoT age briefly. Now the natural question is, will there be any difference from the testing in the past? The answer is yes and no. The answer can be no, because the basic methodology of testing will be equally valid in the age of the IoT. Then why can the answer be yes? The reason is explained using next several slides. In contrast to ordinary office applications, our web services, the IoT applications often involve the IoT nodes of small embedded computer systems. A testing embedded system is very different from testing ordinary applications on desktop and server computers. A target system have very poor resources, and some testing methods cannot be used there. Target hardware is different from the host where the program is written. What is more, often you may be faced with situations where the target hardware is not available when the software is written. Also, setting testing environment in the office and laboratory is very difficult. So basically, our testing is generally difficult for the IoT node. Let me explain the point I raised. The first point is poor resources in the IoT node. The slide shows an IPv6 node based on 6-LoWPAN wireless technology. Please note that a computer has only 64 kilobytes of memory. This includes the stack. When was the last time you have to deal with a program that uses only 64 kilobyte RAM? On Linux and Windows, if you link network library, graphic library, etc., you can easily go up with this limit. The next point is target and host computers are often different. CPU types may be even different. This makes it hard to perform source-level debugging sometime. Cross-development refers to the software development where the source code is compiled on the CPU and the binary files are sent to the target CPU for execution. We have to move the binary object to the target computer after generating them on the host computer. It is an added step, and bugs can creep in the tool chain, such as compiler, linker, etc., when we do cross-development. The photo shows an ICE, ICE. ICE stand for in-circuit emulator. Basically, it acts as a CPU replacement, plugs into CPU socket, or plugs into system bus. Disables the original CPU and acts as it were the original CPU. It has a connection to the host computer, which can control ICE operation, such as step execution, examining and setting memory locations, registers, etc. It can test many things which are impossible to do unless ICE is available. However, the proliferation of many types of CPU has made it rather difficult to create ICE for every CPU. Testing a real-time embedded system is inherently difficult. In the lab or office setting to test the real environment, we may be forced to use simulators to simulate a real-time event due to lack of hardware, etc. But building the realistic simulation environment may be as expensive and time-consuming as building the real environment. Our knowledge of the future IoT application is not sufficient to build a simulator that can mimic the real world completely. I think when people in the audience tackle testing of real-time embedded systems, the difficult issue, they will realize the failure to reproduce behavior of programs, including bugs. Bugs are often timing sensitive, and recreating the original sequence of event in a manner that would trigger the bug again is next to impossible in many cases. This is one of the most difficult issues of real-time embedded systems testing. The next point I raised is setting up complete testing environment in the office or laboratory is difficult. The slide shows a scene from the guidance system in a zoo. There are tags on the cages and path, and the visitors use handheld terminal device to obtain the guidance on the animals and such. To mimic the environment of the zoo in the office or laboratory can be difficult. We can't really mimic the radio wave propagation environment of the zoo in the laboratory, for example. Systems that use short-distance radio wave communication will be popular. Bluetooth Low Energy, BLE, and other technology have caught on. We have our anechoic chamber. That is a dark room for radio wave to test radio equipment without causing interference outside and without interference from outside too. Another example of the difficulty of setting up testing environment is smart house. We can certainly test interaction of only a couple of devices at a time in the lab. However, a useful application in smart house may require more than 2 devices, and setting up such testing environment may be too costly. It may cost as much as building the part of the real smart house. So testing the system in the smart house itself may be the more inexpensive or cheaper alternative. Today, it may be our common knowledge, but when this system for urban street guidance system was tried a dozen years ago, it was not. We had a lot of problems by the radio echoes from passing trucks. Even though large group of people sometimes echoed back enough radio signals. What surprised us was a large amount of illegally enhanced CB radio used by truck drivers. We could not test these in the laboratory. One characteristic characteristics of the testing in the IoT is it requires a holistic approach. This means that certain phase of testing must include all the elements of application, hardware, software, network, and servers on the cloud all together. I know this conference is soft tech, but software testing alone is not sufficient in the IoT age. So testing must involve from the total system point of view, local hardware and software, network infrastructure, remote servers or services. Such holistic approach is essential. This may be very different from traditional testing. Take, for example, a guidance system in a park. This is a garden in Tokyo. What if something goes wrong? What is to be blamed? Is it local hardware of the mobile terminal? Is it local software of the mobile terminal? Is it the tag or marker in the park? Is it the network that connects the terminal to the servers? Or is it the service on the cloud server? The user wants to know where the problem originates and how the problem can be fixed. So testing must cover the scenario to isolate the bug and figure out where to contact for the fix. Here I will mention some part of the IoT testing where traditional testing skill is useful. Our testers are usually asked to test only a customer software module. In the open IoT approach, which I have been advocating, many modules from different stakeholders work together. So either you have to test all the modules together or test that a customer's module conform to a certain API so that the customer's module can be used with other parties' modules. So there are obviously compatibility issues. Standardization is very important in that regard. I believe you as a software testers are awake of the importance and interoperability testing issues. Conformance testing in the age of open IoT will not be different much from the past. As a pioneer in the IoT, I can repeat this. Testing cannot be completed in the office or laboratory of a single player. Field testing will be inevitable. A holistic approach is necessary. In the age of the IoT, while existing testing methodologies can be applied at many phases of testing. As a matter of fact, testing a complex IoT application may involve not only the technology, but even human engineering and social aspect too. The IoT applications sometimes can be very complex, involving many hardware and software modules from many stakeholders. It would be difficult sometimes to identify bugs and isolate the cause of such bugs in a complex system. However, we must find a way to identify the cause and know where to place the blame if the IoT ever is going to be our dependable social infrastructure. It may not be the task of the testers to think about it, but we as an engineering community along with the rest of industry and the whole society must think about it so that the IoT can be useful in the future society. The IoT is no longer a buzzword. It will become part of the social infrastructure to realize many new services. I have described some of them today. Such IoT applications bring new aspects to testing by its own nature. We as a whole society should think about how to identify bugs and place proper blame on parties if the IoT will be truly pervasive and ubiquitous. And here we mean not only testers, but industry as a whole, government agencies and academia, and users can contribute by means of mass error reporting in the IoT age too. Okay, that's all about for today. Thank you very much attending this keynote speech. Thank you very much.
Thank you to Professor Sakamura. And you may catch him at lunchtime if you have questions, further questions. Thank you once again.